Having spent some time thinking about prime numbers, thinking about algorithms to say determine prime numbers or to say make a list of prime numbers, let's now focus our attention on a different problem which is actually related to prime numbers, which is that of finding, let's say, the GCD of two positive integers. GCD is the greatest common divider, which is the largest positive integer which divides both the numbers that we have, which is also known as HCF, highest common factor. Idea is very simple. So for example, GCD of 100 and 80 is 20 because look, 20 is the largest number that divides both 100 and 80. Any number more than 20 divides maybe one of the two, but not both. Likewise, for 120 and 36, the GCD is 12 because 12 is the largest number that divides both of them, right? So there's, when I divide them, there's no remainder left, right? So like a factor, yeah. So basically, highest common factor, the name is quite clear from here, or GCD. 2010 and 1020, the GCD is 30 because no number more than 30 can divide both of them, leaving a remainder of 0. So that's the idea. Now, GCD finding is in fact something we learn as maybe in elementary school mathematics, and the method we are usually taught, right? Usually we learn this thing called prime factorization. So the idea is, you take these two numbers, you decompose them into, let's say, their factors, prime numbers, and then see what are the common factors, and by multiplying them you can get the GCD. So this is something, I guess students learn as part of their elementary training in mathematics. Very nice, clean method. There are some other methods as well in finding GCD, but broadly around the same theme, right? However, when we look at an algorithm to compute GCD, we will rather not do prime factorization because it turns out that prime factorization for large numbers is not very easy. Interesting this is. In fact, a lot of real world cryptography algorithms work just because of this simple fact that factorizing large prime numbers is not at all trivial, even with today's computers. Though we have large computers today, I mean, we have powerful computers today, even then, this is a hard problem. So, for example, our financial transactions with banks, basically the underlying principle is just this, that there are two prime numbers, P1 and P2. I can multiply them quite trivially. Obviously, I can just do that. P1 times P2 is M, but given P1 times P2, it's much, much, much harder to find P1 and P2, which is to say factorize, which is to find, let's say, prime factorize M. So, while in textbook, we might, for simple small numbers, we might do prime factorization. In fact, writing a program to do prime factorization is a good exercise. I encourage you to do that. I think as part of exploration and bonus, but in itself, prime factorization is a hard problem. And let's say a computationally expensive problem. So we are not going to take that route, right? Uh, Given this, let's think of some other algorithm to compute GCD. The most naive method that comes into mind is really by the definition, by the word, let's say GCD, greatest common divider. What we can do is to say that, okay, look, let me start with the smaller of the two numbers because GCD cannot be more than the smaller of the two numbers. So it has to be at least at most as large as the smaller of the two numbers. Let me start from there, and I keep reducing by one and keep checking if I have a number that divides both. Now, clearly, this algorithm is naive, but this is correct. It's going to work, right? So what I mean is, basically, I just find out what is the, let's say, minimum of A and B, which is logical because the result cannot be more than the minimum. So I find the minimum of A and B, and now I run a for loop in reverse order. Notice this range is going in a step of -1. So I keep going result 0, 1. So result -1, result -2, all the way until 0, which means 0 will not be touched, but the last value will be, for test, will be 1, right? And if it turns out that, look, if A modulo test is 0 and B modulo test is 0, if both of them, this is an AND condition, so both must be correct. If both of them are true, then I just say, okay, look, I found my GCD. I'm going to break out of this loop and I return the result. Very logical, very straightforward, but obviously quite naive in this approach, right? Because we're just testing every number, right? But anyway, let's just build this and see what happens. So I get here and I just write, let's say, okay, maybe I put a text box here first, GCD, say, naive approach. And like I said, we can write say a text box here, say def, say GCD naive, uh, so to illustrate that this is a naive algorithm, right? So GCD naive algorithm here is basically takes two arguments, say integers A and B, So these two have to be integers. Again, if you want, you can put some checks on this. You can have some exceptions being raised and so on, but I'm leaving that aside. So I just say A, B are positive integers. Say A, B are positive integers. And we can, without loss of generality, we can also say A is greater than B, right? So I just put this so that it doesn't really matter actually, right? So I just say A is, say, greater than B, right? Now, oops, I think I ran this too early. So I come back to the cell here. Yeah, so I click shift and enter, which made it run. It should only be enter, right? However, remember what I want to do is I want to define a new variable called result, which is min of A and B. So find the smaller of the two, and thereafter run a for loop. So I just run a for loop, say test in range, say range result 0 and -1. Now remember, this is going to be reverse counting, so result -1 all the way until the number test becomes 1. 0 itself will not be touched, right? So that's the way range works, right? So and what is the condition we are looking at? Well, if A, let's say modulo test is equal to 0, and okay, B, this and is important because both of them have to be satisfying this condition. So is equal to 0. If both of these conditions are correct, then I just go and say basically result is equal to, say, test, right? So that is basically I found a number which is dividing both these numbers, and I can in that case just break out from here, and I can then return, let's say, result. Just in case you're wondering what happens if these two numbers are co-prime, well, basically not to worry, because remember, this range is going to test until it becomes 1. At 1, this condition has to become true, right? So because every number is divisible by 1, so this has to become true, and the GCD will just be 1, right? So when I, let's say, run this once, it's clean now, I can start using this. So if I were to do, say, GCD, say naive, maybe say 30, so 120 and say 36. When I run this, answer is 12, as we had seen before. I can try running GCD of 120 and 37. The answer should be 1, because 37 and 120 really don't have any common factors except 1, right? I can now in fact start playing with this. Let's say 1200 and say maybe say 900, right? So the GCD is 300. So it's correct because this algorithm by logic is correct, right? We're just being very, very brute force about it, trying every number. Clearly, this is, however, a correct algorithm, right? So we have a correct algorithm. We will now try to quantify what is the cost of this algorithm, how long does it take to run, and then we'll try to see how we can optimize it. Very interesting. Bytes Algorithms and Olympiad track is meant to go deep into algorithms and explore them systematically in a lively manner. And that's what we're trying to do here. Look at our website, www.ybyte.in, and forever enjoy programming. Take care. Thank you so much. Bye-bye.